So in this video, we're gonna work on a simple problem on Lagrangian mechanics. So here we've got this pendulum with support, and so basically it's a pendulum of mass m and length L, and it's attached to a support of mass big M, which is free to move horizontally on a frictionless rail. And so the first thing we do is we set up the coordinate system. So as shown in the figure, so the horizontal axis is the x-axis and the y-axis is going up. So basically there's no y component for the support big M, and the pendulum has the coordinates x plus L sine theta and minus L cosine theta. And the reason we want the coordinate expression for the position of the system is that we want to be able to derive the velocity if we take the derivative of the position vector. So that's what we do here. So the velocity for the pendulum m is just v little m is d over dt, and the position vector for the pendulum, which is just x dot plus L cosine theta theta dot, and L sine theta theta dot. So the theta dot is actually from the chain rule for taking the derivative, since theta is also a function of time, and the mass of support's velocity is just d over dt x0, which is just x dot. So with these velocities, we can actually write down the kinetic energy for our system, which is this one. Also, we can write down the potential energy, which is just minus mgl cosine theta. So therefore, our Lagrangian for the system is just the kinetic energy minus the potential energy, which is this. So our goal is to find x and theta that minimize the system's energy. So therefore, we write down the Euler's Lagrangian equation, which is partial L over partial x is d over dt partial L over partial x dot, and partial L over partial theta is d over dt partial L over partial theta dot. And the reason we have a system of differential equations is because we have two unknown variables here. And if we plug in the Lagrangian into this Euler-Lagrangian equation, we will end up with the following system of differential equation, which can be further simplified into this. And this is our equation of motion for this system. And if we use the small angle approximation, so let's say sine theta is just theta and cosine theta is 1. Also, we can neglect the higher order terms if theta is really small. And so we will end up with this simplified version of the coupled differential equation, which is this. The first equation basically tells us that x double dot is just minus ml divided by big M plus little m theta double dot, and if we make the substitution into the second equation, we will end up with a equation on theta, which is this one. And the solution to the above differential equation is just theta as a function of t is a cosine omega plus phi. Here we define a and phi to be just two random constants which can be determined from initial conditions, and omega is just square root big M plus little m times g divided by little m times little l. And similarly, we can derive the expression for x, which is minus a ml divided by big M plus little m times cosine omega t plus phi plus b plus c, and again a, b, c, and phi are just constants. And both theta and x exhibit some oscillatory behaviors. Actually use Mathematica to approximate the solution for the system of differential equations, and so the following two figures represent the initial conditions with theta 0 is pi over 6, which is 30 degrees, not so big angle. As we can see, our approximated solution, which is represented in a yellow curve, is really close to the real solution when t is small. And compare this with another experiment where we have the theta 0 is pi over 2, which is tremendously off from the small angle approximation, and as we expected, our predicted solution is far away from the real one.